Hi, in this video we're going to look at some commonly tested distributions. So in each case I'm going to first give you the name of the distribution and then a description of the distribution. And then these are discrete distributions. After giving you the description, we'll talk about a rule for computing the P sub k values, which is the probability that the random variable is equal to k. So those are going to be the values that are going to be in the table on the right-hand side of the table there. So P sub 0 is the probability that the random variable is 0. P sub 1 is the probability the random variable equals 1, and so forth. And so again, I'm going to give you the name and then the description and then the rule for computing the values in the probability table, and then we'll talk about what the expected value is. And of course, remember, the expected value is just the sum product, and we have the notation mu for the expected value. And then we'll talk about what the variance is in each case. And remember, the variance is defined to be the second central moment about the mean. That's the expected value that I have listed at the end there. Or you can use the fact that you could just take the second raw moment and subtract off the square of the first raw moment. Okay, so that's going to be the process in each case when I talk about these commonly tested discrete distributions. So let's start with the names of these distributions. I'm going to list out the names of the distributions that we're going to talk about. One's going to be called the Poisson distribution. We're going to have another called the binomial distribution, which has a special case of the binomial distribution is the Bernoulli distribution. We'll have another distribution called the negative binomial distribution, and a special case of that is the geometric distribution. We're going to have a discrete uniform distribution. We've already talked about that in a previous video, and I'll come back to that later in this video. But we've already talked about discrete and continuous, for that matter, uniform distributions. But in this video, we're only talking about the commonly tested discrete distributions, and these are all listed on the syllabus, in the syllabus for Exam P. There's something called the hypergeometric distribution that we'll talk about, and another multinomial distribution that we'll talk about. Now, the first four of these distributions that I put in bold, those are very commonly tested. I expect you to see a problem like you'll probably see a problem like each one of these, that has to do with each one of these distributions on your exam. The last two distributions, the hypergeometric distribution, well, let me go back. Since these are all commonly tested, what are in bold, I strongly encourage you to know all of these facts above, the rules for computing the P sub k values, the expected values, the variances. You're just going to have to commit to memory the formulas for those, for each of these four distributions. Now, for the last two distributions, the hypergeometric distribution and the multinomial distribution, those aren't tested as often, but they are in the syllabus for the P exam. And what I expect you to see, if you see anything that has to do with these distributions, what I expect you to see is a question that has to do with what the rule is for computing these probabilities, or what is a probability that the random variable is equal to a certain value for each of these two distributions. However, I will give you expected value and variances, for instance, formulas for expected value and variances, and then you can decide whether you want to memorize those, commit those to memory or not. Now, those are the distributions. I'm going to reorder them, and I'm going to reorder them this way. Same distributions, I'm just ordering them in a different way. I'm going to put the discrete distribution first, and then the binomial, multinomial, hypergeometric, negative binomial, and then the Poisson. The reason I'm listing them this way now is that this is going to be actually the order in which I'm going to present the material to you. And there's a reason for this. So if we look at, for instance, if you look at, say, distribution number 2 is the binomial distribution, and distribution number 5 is the negative binomial distribution, and you might say, oh, well, those must be kind of related to one another. No, you'd be wrong. They're not. Whoever named these, I'm sorry that they did this to you, but whoever named these distributions just made they were just mean. It's just a mean joke. The binomial and the negative binomial are not related. They're different types of distributions. You see the special case of the special case of the negative binomial distribution is a geometric distribution. And above that, number 4, there's a hypergeometric distribution. Oh, well, those must be related. No, they're not. They're not. So that's, again, a horrible choice of words, in my opinion, as far as naming these distributions. Just a mean joke. The hypergeometric distribution and the geometric distribution are very different distributions. In fact, the hypergeometric distribution is more closely related to the binomial distribution than it is to the geometric distribution. If it sounds like I'm babbling, I feel like I'm babbling too. But you'll get, we'll go through all of these descriptions and talk about this in more detail in later videos. So you see number 3 is a multinomial distribution. You might say, oh, well, based on what you've just said, the multinomial distribution probably has nothing to do with the binomial distribution. No, you'd be wrong. Actually, they do. The multinomial distribution is an extension of the binomial distribution. So the binomial distribution is going to be listed second. I'm going to cover the first distribution, discrete uniform distribution. I'll do that today. Or in this video, I should say. And then binomial distribution we'll do in a different video. Multinomial distribution is an extension of the binomial distribution, and hypergeometric distribution is also related to the binomial distribution. So that's why they're in this order that I have. So again, there's a reason I'm going to put them in. I put them in this order because that's it's kind of more natural way to introduce the material. Finally, the Poisson distribution at the very end. Remember, in the listing of how I expect you to see which distributions I expect you to see on the exam, I put the Poisson distribution first. However, it's listed last here. It's just different than all the other distributions. So I'm going to present it last, but it's probably more commonly tested than any of these other distributions. Okay, so let's get started then with just the first one here, the discrete uniform distribution. And again, we've talked about this before. And the discrete uniform distribution that I want to focus on is the one whose support is 0, 1, 2, 3, and so forth, up to some ending value. So the smallest value that the random variable can take is a 0 in this case, and the largest value that the random variable can take is a n minus 1. Notice that there are n values in the support of this random variable. So again, this is an n-point discrete uniform distribution. It's a discrete uniform distribution on n points, not only on n points, but on the n specific points 0, 1, 2, 3, all the way up to n minus 1. That's n points. I'll go ahead and tell you why the main reason that I'm using this support for this distribution is that you're studying for an actuarial exam, and the actuarial mathematics is very applied mathematics. And most of the discrete distributions that we're going to be seeing, they're random variables, they correspond to random variables that represent something. And so all of our random variables represent something. If you're taking a statistics class, they'll just say, oh, well, let capital N be a random variable. No, for what we do, capital N is a random variable that represents something. And so what the discrete distributions most often represent is, they're called frequency distributions. What they most often represent is how many claims are submitted over some time unit or over what's called an exposure unit. And so how many claims arrive each 6 months for this insurance policy? And there could be 0 claims, so we start with a 0. So that's why I'm using the support of a 0 and then a 1 and then a 2 and so forth, because of the applications, the actual applications of these distributions. So all of the distributions, in fact, I'll make this comment. All of the distributions that I listed before, I'm going to present to you in a way that their support is 0 and then 1 and then 2 and so forth. Okay, support doesn't start with 1, support starts with 0. Okay, now that was the name, is the discrete uniform distribution. I would also add to this that this is on n points, and the n specific points 0, 1, 2, all the way up to n minus 1. So the description. Well, the description for a discrete uniform distribution is that all outcomes are equally likely. So if all outcomes are equally likely, when we look at probabilities, all the probabilities have to be the same. There's n of them. They have to add up to 1. And so each probability is a 1 over n. So that's what's defining a uniform distribution. All the probabilities are the same, and they're all equal to 1 over n. The expected value here for this distribution, this specific distribution whose support is 0 and then 1 all the way up to an n minus 1, the expected value is an n minus 1 over 2, and the variance is an n squared minus 1 over 12. That's not a typo in the denominator. It really is a 12 in the denominator. So n squared minus 1 over 12. So another byproduct of listing out the support as being 0, 1, 2, all the way up to n is that you get these kind of nice formulas for the expected value and the variance there. Okay, so now let's look at an example, because the examples are probably, or the type problem that you're going to see probably does not have a random variable that's uniformly distributed on 0 and then 1 and then 2 and so forth, but some other values. So this example 1 is an illustration. Determine the expected value and variance of the random variable that is equally likely to take on the values 11, 12, 13, and 14. Well, equally likely to take on those values means it's a discrete uniform distribution on those values. So it's I'm going to use not a capital N that I've been using before for the uniform distribution on the points 0, 1, 2, and so forth, but this is on different points, 11, 12, 13, and 14. So I'm going to use an N tilde here. But I would still call this, there's still 4 points there, so this is a 4-point discrete uniform distribution. Now my standard 4-point discrete uniform distribution is what I've been calling N, and it's on the points 0, 1, 2, and 3. And I know I'm seeking the expected value and the variance. So for this N, the expected value is, the formula is n minus 1 over 2, where n is just how many points you have. So that's 4 minus 1, or 3 over 2, which is a 1.5. Again, n is just how many points do you have in your distribution. And then the variance is n squared minus 1 over 12, and so that would be 4 squared, or 16, minus 1, 15 over 12, or 1.25. So now what I recognize, those aren't the values that I seek. I seek the values of the expected value and variance of the random variable, the uniform random variable on the points 11, 12, 13, and 14, so on n tilde. But what I recognize is that the n tilde random variable is the n random variable plus 11. Take 0 plus 11, 1 plus 11, 2 plus 11, 3 plus 11, or the 11, 12, 13, and 14. And so it's going to be very valuable for you to be able to write one random variable as a function of another random variable like we've just done here. And so that's why I'm kind of introducing it here in this kind of an easier case, but it's going to be very valuable later on to write random variables as functions of other random variables. Okay, so let's use some properties of variance then, and the expected value of n tilde would just then be the expected value of the cap n plus 11, and properties of expected value is I could take a term-by-term expected value, and expected value cap n. So I get expected value cap n plus 11. The expected value of 11 is 11. And then the expected value of cap n is 1.5. So I'm just adding 1.5 to 11 to get getting 12.5. Now the fact of the matter is, when you have a uniform distribution, you can always just take the average of the values to get the expected value. That's the easy thing to do. But again, being able to write one random variable as a function of another random variable is going to be valuable later on. So I wanted to go ahead and introduce it here. But again, if you're dealing with discrete uniform random variables or distributions, then just take the average of the values. That's the easiest way to get the expected value of the random variable. Okay, now what about the variance? Well, again, look at I'm looking for the variance of cap n tilde. And in red there, I see that cap n tilde is cap n plus 11. So the variance of cap n tilde is the variance of cap n plus 11. Oh, but remember with properties of variance that the variance is translation invariant, which means adding that 11 to cap n is not going to affect the outcome of the variance. So the variance of cap n tilde is actually the same as the variance of cap n, and it's 1.25. Okay, so those are my answers. 12.5 would be the expected value, and 1.5 would be the variance. Let's look at a little bit more complicated example, still discrete uniform, but let's determine the expected value and variance of the random variable that's equally likely to take on the values of 1,500, 2,000, 2,500, 3,000, and 3,500. So now I'm dealing with a discrete random variable, cap n tilde, on, again, it's just a 5-point set, but it's on these 5 points. And what I'll do again is I'll relate it back to the basic, the standard 5-point discrete uniform distribution on 0, 1, 2, and 3, because there I know the formulas for the expected value and the variance. The expected value of cap n here is n minus 1. N is the number of points in your set there. So it's 5. So 5 minus 1 divided by 2 is 4. And then the variance is n squared minus 1 over 12, which plug in an n of 5 and you get 24 over 12. Actually, you get 2, so you get the expected value and the variance are actually the same for this 5-point basic or standard discrete uniform distribution. So now what I'd like to do is, well, what's, again, this is valuable stuff for even later on, so let's introduce it now. How would I get n tilde? What would be an expression that defines n tilde in terms of cap n? So what I do here is I first look at the points for n tilde, and I recognize that they all have a common difference of 500. They're 500 apart from one another. So there's a common difference of 500. So that tells me that cap n tilde is going to be 500 times cap n plus something. And so now how do I get the plus something? Well, you just pick out a value from cap n and see what it is assigned to for cap n tilde. So for instance, I've highlighted in green that 0 should be assigned, a 0 for cap n should be assigned 1,500 for cap n tilde. And if you look at this expression, cap n tilde equals 500 times cap n plus something, we'll plug in a 0 for cap n, and 500 times 0 is 0, and then I need to add what to get 1,500? Well, I need to add 1,500. And then that's going to be my expression then. That's how I'm going to define cap n tilde as a function of cap n. And then, of course, you can check yourself. Let's just pick like 4 needs to be, the cap n value of 4 should be assigned to the cap n tilde value of 3,500, and plug in a 4 for cap n, and you'll see 500 times 4 is 2,000 plus the 1,500. Yes, I get the 3,500 for cap n tilde. So I have the correct expression here. Okay, so now I want to know, well, what's, I'm seeking the value of the expected value and the variance of this cap n tilde. So the expected value of cap n tilde would be the expected value of 500 times cap n plus 1,500. Use properties of expected value. I know that expected value of cap n is 2, cap n being the 5-point standard discrete uniform distribution. And plug in a 2 for expected value cap n. I get 2,500 for the expected value cap n tilde. But again, notice that's just the average of all the values. And then finally, the variance of cap n tilde would be the variance of 500 times cap n plus 1,500. The plus 1,500 is not going to affect the outcome for the variance calculation, because it's a variance is translation invariant, so it's just the same as a variance of 500 times cap n. But 500, how do we factor out the 500? So we know from properties of variance that the 500 gets factored out as a square, so it's just 500 squared times the variance of cap n. Variance of cap n was 2, so 500 squared times 2, I get a final result. 500,000 is my final answer. Well, it took a while to get there, but 500,000 is my final answer for the variance of this cap n tilde, the discrete uniform distribution on those 5 points. Finally, let me make one more observation with another example. Let's say that these are my values and they're equally likely to occur. So I've got a discrete uniform distribution on 3 points, 1,500, 3,000, and 6,000. Notice that there is no common difference in those values. And so I'm not going to be able to use any sort of process that I did before, like in example 2, because there's just no common difference there. So the only thing that you're left to do here is just write out what the table would be. So it's pretty easy table to write out. The values, the support for cap in tilde are 1,500, 3,000, 6,000, and they're equally likely, so that means their probabilities all must be equal to 1/3. And then if I wanted the expected value and the variance, you just got to do it. The expected value is just going to be the sum product there. Notice that's just going to be the average of the values again. And then the variance is going to be, well, this is one way to calculate the variance, is take the second moment of the discrete distribution that you have the table for there and subtract off the square of the first moment. I'm going to leave it to you to show that those values are 3,500 and 3.5 million respectively. Okay, so that does it for this video, and I'll see you in the next one.